Okay, welcome back. There were two worksheets that passed out when we were back at school, and I posted for you to do them. They were called Differentiation Review Worksheet and Extra Differentiation Practice. They were two worksheets with essentially just a bunch of problems involving knowing how to differentiate functions and being able to use the chain rule, product rule, quotient rule, and just kind of knowing all the rules. I don't know which ones of these are really worth going over. There's an answer key to this worksheet so you can see exactly what I did. But I might just do a couple of these right now, and I'll say a couple of helpful things a little bit. So this is 5 over b squared minus x squared squared. This is a kind of problem where, I don't know, experienced professionals will see what the good thing to do here is, and that is to rewrite this thing. You definitely don't want to use the quotient rule here because the top is so simple, it's just a number. So I think you'd sort of be wasting your time. The skilled way to do this is to recognize that this is really just 5 times b squared minus x squared to the negative 2. And then this is really just a straightforward power rule, chain rule problem. And so, okay, now we go to take the derivative. Well, what is the derivative? 5 times something to the negative 2 should be 5 times negative 2 something to the negative 3 back inside for the derivative of the something. And what is the derivative of b squared minus x squared? B is just a constant, so the derivative of that is 0, so that's just negative 2x. And so then if you want to simplify this, and I do, I have negative 5 times negative 2 times negative 2, so that's negative 20, so I get negative 20x, and personally to me, I always rewrite things with no negative exponents, and so that would be the way I would leave that problem. Have I made some kind of mistake here? Oh yeah, that negative 5 just was a figment of my imagination. So it's just positive 20x. Okay, good. I have no idea which ones these are worth doing. Or maybe I'll just do like 2 more. Yeah, I don't know. Something like number 9 from the back. Here, again, this appears to be kind of an annoying problem because there's this like cosecant in the denominator. Who can remember cosecant anyway? But you know what? This is really just x sine squared, and that to me is like a much simpler way to deal with that problem. So a similar kind of theme. And so the derivative of this is just going to be via the product rule, derivative of the first times the second, so 1 times sine squared plus the first times, what is the derivative of sine squared? Well, the derivative of something squared is 2 something to the 1 back inside for the derivative of the something, and so we get this. And so final answer, sine squared x plus, here it's tempting to just apply the trig identity and write that as sine 2x. So people will sometimes do that in that situation. But I didn't on the answer key, so whatever. You could also just factor the sign. I guess it depends on what you're trying to do. Okay, maybe we do one more, or maybe we'll just stop. Okay, let's move on to the other worksheet, which I found kind of more interesting. So the other worksheet called Extra Differentiation Practice, the very top of it, this might be the hardest thing on all of these worksheets because it does involve sort of thinking and understanding. And it's something we did, but you know, it was a month ago now, basically. So you're just sort of presented with all of these limits, and you're just told, you know, do them. So for example, let's start with number 3. Number 3 says, what is the limit as x approaches pi over 3 of the secant of x minus 2 over x minus pi over 3? Okay, and the first thing to observe is that this is just a limit. And so you might think, oh, why don't we just like do the limit? You know, if I didn't know even anything about differentiation, or even much about calculus, maybe I just try to do the limit. Well, of course, if you plug in pi over 3, you're going to get a 0 on the bottom, and secant of pi over 3 is 2, so you're going to get a 0 on the top. So this is a 0 over 0 situation, and therefore I can't say immediately what this limit is. And in fact, it's going to be quite tricky. You could try tricks, multiplying by the conjugate, splitting it up, doing all kinds of weird things like that back from the limits unit. But none of those are really going to go anywhere, probably. And anyway, they're not how it was intended that you do this problem. The way it was intended that you do this problem is that you recognize that this is just a derivative. So this assumes that you are kind of an expert on the definition of the derivative, and that you're so good at it that you recognize the definition of the derivative when you see it. And so what is the definition of the derivative? Well, okay, we did this a million times, but we can do it again. So you have some function f, and you have some point a on that function, and that point is a comma f of a. And the original way we saw we're exposed to the derivative is it's the slope of the tangent line to the curve. And how do we find the slope of the tangent line to the curve? We use an extra point. So we just call this other point like x, and we go up here to x comma f of x, and then we look at the slope of the secant line, which goes through those 2 points. And this marker's dead. And then we move those 2 points infinitely close together, and when we do that, we will this blue secant line will become the red tangent line. Okay, and then we can just look and see what is the change in y. It's f of x minus f of a. What is the change in x? It's x minus a. And so if we take the slope of the blue line, which is f of x minus f of a over x minus a, and we just move those 2 points infinitely close together, then the slope of that blue line will equal the slope of the red line. And so this is the limit. We take the limit as x approaches a by moving those 2 points infinitely close together. And this, by definition, is f prime of a. So for this problem, we see, oh, this is one of those situations. This is just a derivative. What derivative is it? Just by kind of comparing it or via understanding with that, we can see that it's the derivative of secant at pi over 3. And if you want a kind of a better picture of this, we can, graph secant, surely. So that's pi over 2. Now if we, this picture will be a little bit smushed, but if you go over here to pi over 3, what is the secant of pi over 3? Well, it's 2. And so, contrary to this sort of bad picture, so you have pi over 3 comma 2. Alright, maybe I'll just stop there. Or maybe I'll just try to do a good job. Okay. Second try, that's 1, that's 2, and over here at pi over 3, the value is 2, and by the time we get to pi over 2, we're off at infinity. And so this graph is looking like this. Okay, and if you want to find the slope of the tangent line there, then you just find the slope of the secant line and you move the 2 points infinitely close together. And so, indeed, you have the change in x, which is x minus pi over 3, and the change in y, which is secant of x minus secant of pi over 3, which is 2. Uh-oh, crying baby. So what is this? What is this lit? The answer is that this limit is just whatever the slope of the, whatever the derivative of secant is at x equals pi over 3. In other words, and we did this from the very beginning of this unit, we recognize this limit as a derivative, and therefore that the answer to this limit is going to be whatever the derivative of secant is at pi over 3. In other words, whatever the slope of the tangent line is there. Okay, but what's new is that we just know the derivative of secant. The derivative of secant is secant x tan x. And therefore, I can just plug in pi over 3 into secant x tan x, and I get secant of pi over 3 is 2, tan of pi over 3 is root 3, so we get 2 root 3. And since 2 root 3 is the derivative of secant at pi over 3, then it means that this limit just is 2 root 3. And that's it. The answer is a number. Okay, going a lot faster now, for number 4 is basically just the same thing, but a little bit more complicated. Here we're taking the limit as x approaches 27 of the log base 3 of the cube root of x. All kinds of family members in this video. Hi Ada. Making a math video.
Okay, let's go back
So again, this is a limit. The answer to this limit should be a number. And I don't know what that number is, and I don't have any techniques to be able to come up with the answer to this limit. So, what do? I understand that this...
No!
Ada can stay here for a minute, I guess. I understand that... Ada, can you have a seat over there?
Oh, yeah.
Okay, and watch. Okay, I understand that this limit is a derivative. And what is it the derivative of? Well, if I understand the definition of the derivative really, really well, then I see that it must be the log base 3 of the cube root of x function. And at x equals 27. And indeed, if I plug 27 into log base 3 cube root of x, I get, well, the cube root of 27 is 3, log base 3 of 3 is 1, and so 1 is indeed the y value, the f of a. Okay, and therefore, the answer to this problem is just whatever the derivative of the log base 3 of the cube root of x function is at x equals 27. And so I can just take that derivative. What is the derivative of log base 3 of cube root of x? Sounds kind of hard, but we can do it. I just know this, so the derivative, okay. So let's see, if I write this function as log base, log log base 3 of x to the 1/3, then the way to do this, I guess, is maybe to bring down the 1/3 first of all, and then also to recognize that log base 3 of x is really ln x over ln 3. And having done that, now I can differentiate this more easily. Yeah. So what is this? This is going to be 1 over 3 ln 3. Ada, you're in the video. 1 over 3 ln 3 times the derivative of x. Okay, and so finally, I now just plug in 27. And when I plug in 27, I get 1 over 81 times ln 3. I hope that's the right answer, yeah. Oh boy. Something got wrong? No, I guess that's okay. Is that the same thing as 3 cubed? Yeah. So there are many different forms to write this in. On the answer key, I put something a little bit different, but it's equivalent. 3 cubed, yeah. Okay, but the big picture is I have to understand that this limit is just a derivative. Okay, so that's 3 and 4. They're numbers. 1 and 2, I'm just gonna like push on here and finish this. For numbers 1 and 2 on this same worksheet, they're asking a little bit of a different question. And that goes back to the other way of thinking about what a derivative is. Or rather, it's not different, it's just more. Let me just erase this really quick. Alright, so this is like a derivative at a point, which is a number, but we also have then the derivative function. And what is the derivative function? It's the function which outputs derivatives. And so if you give me some function and I want a general formula for the derivative at x, then the logic is exactly the same. You take x comma f of x, you pick a point which is a little bit more than x, you call it x plus h, So this point is x plus h comma f of x plus h, and then you find the slope of the tangent of the secant line through those 2 points, and that will be f of x plus h minus f of x is the change in y, and the change in x is h. So that's the slope of that purple line, and then if you move those 2 points infinitely close together, then you will get the slope of the tangent line here. In other words, when you take the limit as h approaches 0. Okay, so what is this? It is the general formula for the derivative of f. Hi, Ada. Okay, so that means for number 1, what are we doing here? We're taking the limit. You're just presented with a limit kind of out of context, and you have to figure out what's going on. The limit as t approaches 0 of e to the tan x plus t, little parenthesis mistake there, minus e to the tan x all over t. And you should take one look at this limit and realize a couple of things. One, it's definitely a derivative, right? Just by compare and contrast with the thing I just did over here, clearly this limit represents a derivative. But unlike, unlike the other examples that we just did, which were derivatives at a point, and so the limit is a number, here this limit is not going to be a number. This limit is going to be a function. Okay, well, what function? This is clearly just the derivative in general of e to the tan x. Another way of putting it is just to say that if you were given the problem of finding the derivative of e to the tan x on like the second day of this unit on differentiation, when all you knew was how to do derivatives using the definition of the derivative, then you would have gone straight to this limit as the way to solve it. And then you probably would have gotten stuck because there are no methods for doing this. But we have methods now. We know exactly how to differentiate e to the tan x because it's just a chain rule problem. The derivative of e to the something is e to the something back inside for the derivative of the something. And here, that's just the answer. Okay, and finally, number 2 is basically the same. This is the limit as h approaches 0 here. The variable is even reminding you of what's going on. Cosine x plus h squared minus cosine x squared all over h. So what is this? Of course, it's just the derivative of the cosine x squared function. And how do you take the derivative of the cosine of x squared? Well, the derivative of cosine of something is negative sine something back inside for the derivative of the something, and the derivative of x squared is 2x. And so there we go. It's just minus 2x sine of x squared. Okay, the rest of this worksheet is just a whole lot of more problems of just doing derivatives, man. So I don't know if we need to go over any of these, so I just won't, and I'll let you just check the answer key online and learn for yourself that way. Okay, good. Hopefully that helps, and you'll be hearing from me again soon with more stuff.